Hi, today's video is about finding information from logistic growth curves. Now, logistic growth curves are really important in the real world and very relevant to the time that I am right now recording this video for you. So I'm going to start on the back by just giving you some general information about logistic growth curves. So a logistic growth curve is basically a parent function. Like a parabola is a parent function, cubic, a quartic, a square root graph, y'all know a bunch, logarithmic. Okay, there's a bunch of logistic growth curves. So there's a general shape that they usually have. So I'm going to sketch here x and a y axis. And on our logistic growth curve, there are two horizontal asymptotes. Usually the lower one is on your x-axis. So I'm drawing it slightly above just so you can see it. But most cases, your lower horizontal asymptote, y equals a, is going to be your x-axis, because usually the lowest the quantity can get is 0. So even if it starts above it, it's going to trend toward 0 if you go on the other side of your y-axis. Then there's also an upper asymptote, and this upper asymptote is y equals b. So exactly midway between your upper and lower horizontal asymptotes, there's going to be a point on your graph that is called the inflection point, which is a vocabulary word we learned earlier this year. Now, that's where the graph changes its curvature. If you'll remember, inflection means it's going to change concave up to concave down, or concave down to concave up. So in the logistic growth curve, it's going to head toward the lower horizontal asymptote, normally on your left. It's going to curve up. It is concave up here. See it? It's like a bowl. Concave up. And then at the inflection point, it's going to turn around and it's going to go concave down. Concave down, like a rainbow. So this is the general shape of your logistic growth curve. Some things you should notice. The curve is always increasing. Okay, it's going up. It's not going up at the same rate, but it is going up on the entire domain. Even over here on the right, where it's getting kind of more flattened out, it's still going up. It's just going up a teensy tiny little bit. Okay. Also, the rate of change, or derivative, is always changing. In other words, your slope is not 0 anywhere. It approaches 0 on both ends, but it's always changing. So your inflection point is always halfway between these asymptotes. So you can find the y-coordinate of it. If you know the x, it's another story, but to find the y-coordinate, you can take your upper asymptote b minus your lower asymptote a, which is often 0, and then just divide it by 2. And that will help you to find the y-coordinate of your inflection point. So that's like a little formula you can use to find that. You can also, I'll label this is your inflection point. You can also find your inflection point by setting your second derivative equal to 0. Now, why did I do d2p over dt squared instead of y and x? Because a common application of logistic growth is population over time. So a very common dependent variable is population, and a very common independent variable is time. So let's take a look at the derivative graph for this. So I'm going to sketch a little X and Y axis. So I'm ready. Let's go back and see if we can figure out some information about this. Over here on the left side, the derivative would mean the slope. The slope is getting very close to what value on the left? Hope you're seeing it going horizontal, which would mean 0. And up here on the right, what is our derivative getting really close to? Do you see it flattening out? It's getting closer to 0. Not exactly 0, but pretty close. So what you're going to see is you've got this horizontal asymptote on your derivative graph where the slope is close to 0 on the left and on the right. So it approaches the horizontal asymptote on the left and the right. Now, what happens to my derivative here? It's getting the slope. The slope is getting steeper and steeper and steeper and steeper and steeper and steeper and steeper till it reaches its highest value at the inflection point, and then it starts to tilt down and it's getting less and less and less and less and less and less and less. Flatter and flatter and flatter and flatter and flatter and flatter. So what you see on your derivative graph is that it has a maximum value, and that maximum value is your maximum slope, and the x-coordinate underneath that is going to correlate to the x-coordinate of your inflection point, or the time that you hit that is going to be the same time that you hit this maximum on your derivative graph. Now, there is a general formula for the derivative of the equation, and we often in calculus work with this more than the regular logistic growth equation. dp dt is equal to kp times L minus P. Now, this L is called the carrying capacity. And this carrying capacity is the same thing as the upper asymptote. So if they give you the equation in this form, or if you could algebraically manipulate it so that it lands in this form, now P could be a Y, okay? So this is in terms of Y instead of X, but as a derivative, you know, sometimes we have derivative equations in terms of either variable. So if you get your Y here and then here by this one by itself inside of the parentheses, then whatever is leading right here minus the Y or minus the P is going to be your upper asymptote, your carrying capacity, so you can recognize it quickly. Now, why are logistic growth graphs important? Well, for a lot of reasons. This left side of the logistic growth curve looks very much like an exponential growth model, okay, and they can get pretty steep. I mean, they don't have to be as flat as this one that I've made. So they grow, it's like something is growing exponentially. But it doesn't grow exponentially forever, because let's think about it in the real world. What things grow exponentially? Think back to when you were in Algebra 2 and you studied exponential growth models. What kinds of equations did you use? What kinds of real world data or scenarios did you use? A lot of the time they'll do like bacteria or, you know, something, it's just like things that grow really quickly, germs often. So do they grow forever? No, they don't. Eventually, they're going to run out of room, or they're going to run out of food, or space, something crowding, overcrowding. They usually, at some point, quit doing their exponential growth thing, and they kind of level off to a level in the population that's actually sustainable over time. So, logistic growth curves are often a better model than exponential growth models for real-world scenarios. So populations of bacteria and things like that, they don't grow forever. Another important aspect of logistic growth modeling is in business, which is a large reason why a lot of business degrees require calculus credit in order to get that degree. I'm going to tell you a little story about somebody you may have heard of before, Sam Walton. Sam Walton is the man who created Walmart stores, and he had a good understanding of logistic growth curves. And what he did was he used the logistic growth curves to make sound and very smart business decisions. So he would see things like high ticket items, like expensive things like a new TV or a new video game console or something that costs quite a bit of money even for the Walmart store to get its hands on. And when they first came out, well, barely anybody knew about them, so they weren't selling. But as soon as like advertising picked up and things, they'd start flying off the shelves. And there would be like, oh, we're selling them like crazy. We're making tons of money. But they don't fly off the shelves forever. Eventually, the number of items being sold they're still increasing here, but it's more than it used to be, but it's not growing as fast as it was. And eventually, it just kind of steadies off to like people replenishing the supplies that they have in their home, and they don't really grow that much anymore. It's just regular purchasing. So what he did was he figured out that if he could chart the sales of these high dollar ticket items, as soon as he saw the rate of change decreasing over time, so he's looking at the second derivative here when it switches from concave up to concave down. As soon as he saw that it was concave down here, he quit purchasing new ones from the suppliers. And he just said, we're going to sell what's on the shelves and we're not going to get any more. And so they would let the product go out, and they wouldn't end up with all this overstock that they had to take for a loss or put on major sales and maybe even take, you know, some loss in their profits from. So his ability to study sales with relation to the logistic growth curve really allowed him to make some very great business decisions, which obviously have made him very successful. So another application of the logistic growth curve is the COVID-19 cases. So let me see if I can back this up so you can see my little graph I printed out here for you. This graph, here we go. Total confirmed COVID-19 cases. How rapidly are they increasing? So if you notice, the y-axis here is not scaled linearly. Like it's not 100, 200, 300, 400, 500. It's not 1,000, 2,000, 3,000, 4,000. It's 100, then times 10, 1,000, then times 10, 10,000, then times 10, 100,000, then times 10, a million. So this is really steep exponential growth going on here. So steep that if you were to put them all just like in hundreds, it would go way off the page, which is why they have to change the scale, because this exponential growth is insane. And this graph is updated on May 14th. So that's today's date. So this is live data for when I'm recording this. And the source is this European Center for Disease Control. So people who are outside of our political sphere. So anyhow, you can see that the United States has got the steepest growth on this logistic growth curve that's going up. And you can also see that it is starting to flatten. You keep hearing about flattening the curve. Well, that's where we reach that upper asymptote where the number of confirmed cases is remaining steady. So you may be seeing it increase just a little bit over time, like, oh, there's a few people still getting it, but it's not as much as it was. So that's why they keep talking about flattening the curve. Now, that doesn't mean more people aren't still getting sick, but it just means that the growth is not so skyrockety high exponential growth stuff as what it was previously. So obviously, the people who are studying this data and who are making predictions and modeling are using a great deal of calculus, and it's an extremely important skill in order to make real world decisions about shutting down businesses or schools like we have encountered. So anyhow, just wanting to give you some information about why this is an important topic of discussion. Whoa, sorry. Now, we are going to do some problems that are not real world, that are just for fun because we like math and we want to learn about logistic growth. So, number one, A ship carrying passengers has the misfortune to be shipwrecked on a small island from which the passengers are never rescued. Do you see that real world? No. It's just for fun. The population of the island after time t in years is given by the following logistic equation. P of t is equal to 5,780 divided by the quantity 1 plus 4.78 times e to the negative 0.4 t time. This is, by the way, a calculator problem. I don't expect you to be doing all that math in your head. So, part A, what is the maximum number of people that the island will support? So they're basically asking, what is that upper asymptote? What is the carrying capacity? What is the greatest number of people that we could have? Well, if you think about this negative 0.4 t, this value e is just going to be like an exponential decay. And we're multiplying it and adding some number. So anyways, these are just going to take this 5,780 down. You divide by a number, you're going to take it lower. So we would say the carrying capacity the most is whatever's here in the numerator, 5,780. We can't have more than that because if we divide by some number greater than 1, it's just going to create a smaller population. So what is the initial population? Well, the initial population would be like, what is the population when the time is 0? So if I plug a t in for 0 and then do the arithmetic, this is e to the 0, so that's just 1. And if I add 1 plus 4.78, that's 5.78, which happens to be very close to the number in the numerator. So 5,780 divided by 5.78 means that would equal P of t of 1,000. And feel free to use a calculator if you'd like to. C, what is the population after 10 years? So that means if t is 10, what is P of t? What is the population going to be? P of 10. So we just plug a 10 in here and work it out with the calculator if needed. And it does come out to 5,315 people. Now, how long will it take the population to reach 3,000? So that's like saying when P of t is 3,000, what is the time? So that equals 5,780 divided by 1 plus 4.78 e to the negative 0.4 t power. So what we're going to do is get the t by itself, which we could do algebraically, or since we have the graphing calculator, another way to do this is to go into your calculator, put 3,000 in y1 and the right side of the equation in y2, and then look for the x coordinate, because we're looking for how long, that's like the time, the t, the x, of the intersection of those two. So you can do that two different ways. I think since it's a calculator problem, it'd be faster just to do it graphically. You're probably going to have to change your y max to something bigger than 3,000 so you can see where they intersect, because they're going to intersect at a y value of 3,000. And doing so, you should get a time equal to 4.102 years. You may want to pause your video and do that in your calculator. Make sure that you can arrive at that answer. And of course, let me know, email me, call me if you have questions. Okay, come by and see me. Well, no, not in COVID-19. So, E, when will the rate at which the population is increasing begin to decrease? So that's talking about where is this inflection point. And if you'll remember, we talked about upper asymptote minus lower asymptote divided by 2 will give you the y value. So the carrying capacity, the upper asymptote, is 5,780. And if you subtract the lower one, which for a population, the lowest it could go would be 0, and divide by 2, you're going to get 2,890. So If you do the same thing you did to solve part D, set 2,890 equal to 5,780 over the quantity 1 plus 4.78 times e to the negative 0.4t power, and solve for time by looking for the x-coordinate of the intersection of those two equations, y equals the left side and y equals the right side, then you will get a time equal to 3.911 years. So that is when the rate at which the population is increasing will begin to decrease. Now, what is the rate at this time? Well, we can do that using the calculator as well. Let's see here. Y equals, I'll go ahead and put this equation in, 5,780 over 1 plus 4.78 times e to the power of negative 0.4t. So let's see, I'm going to go ahead and get that 3.911 on my screen, just in case y'all had any problems with those. So I got that in here. I'm going to go window, Y max 3,500, count by 500s. I don't really need negative time. We could start at 0. We're looking at the times being smaller than 10, maybe 5 is good enough. Let's hit graph and see what we get. So this is a little piece of our exponential growth model, and then we've got the constant, the y equals 2,890, also graph there. So we want to find the intersection. Second, and the trace button for calculate menu, option 5 for intersect. I'm going to arrow close to the intersection point. It says first curve, enter, yes, that's my first curve. Second curve, enter, yes. Guess I don't care, press enter again. There's my 3.9111 that I wrote down as the number of years. Okay, so now I want to know what is the rate, the derivative at that time. So I'm going to just take out this other equation, or maybe I'll just press enter on it to make it not show up. So here, this is my logistic growth equation. I want to know its derivative at that time, 3.911. Okay, so I'm going to go second, and then trace button for calculate. I want the derivative, which is number 6, and then x equals, I'm going to put x, which was the last x value my calculator calculated, which was that 3.911. And 534. Hang on just a second. dy dx, x is 3.911. No, there we go. So it did not remember my value, I think, because I regraphed it. But the dy or dp dt such that the time is equal to 3.911 is 570, let's see, that's a lot of 9s. That's going to round it up to 578. And what units would this be? The rate that the population is decreasing? No, the rate at which population is increasing when it begins to decrease. So this would be people per year, because our time is measured in years and the population is given by P. So there we go. All right, number 2. The logistic growth equation dp dt equals 0.006 p times the quantity 200 minus p describes the growth of population P where t is measured in years. What is the carrying capacity? So this equation is in the form like I showed you down here. So our carrying capacity is the number in the front of the parentheses minus the p. So that's going to be 200 because this equation is set up already in that form. Now B says, what is the population when it is growing the fastest? So, what is the population when it's growing the fastest? So what is the y value at that point of inflection where it's at the most rapid growth? So that's your b minus a divided by 2. And if we're talking about population, the lowest of population could go at 0. So you do your upper asymptote, 200, minus your lower asymptote, 0, divide by 2. So that is 100. The population is 100 when it is growing the fastest. C. What is the rate at which the population is changing when it is growing the fastest? So the rate is the derivative. And when it is growing the fastest, it's growing the fastest when the population is 100. So we're going to plug 100 in for the p-values in the derivative equation. So dp dt equals 0.006 times 100 for that population times the quantity 200 minus 100. So that's 100 times 100 times 0.006, which will give us 60. And they don't really give us units in this problem, so we don't need to use units. All right, here we go. It's our last one. The number of fish in thousands in a particular lake at the time t in years is given by the differential equation dy dt equals 0.8 times y times 8 minus y over 8. A. On the slope field, sketch the particular solution for the initial condition of 1,000 fish in the lake. Describe what happens to the fish population as time goes by. Okay, if I start with 1,000 fish in the lake, notice the y-axis is in thousands of fish. The x-axis is time in years. And we want to start with 1,000 fish in the lake. So if time is 0, starting with 1,000 fish in the lake, 1,000 would be at the number 1. So now I want to try to sketch out the slope field on this graph, the particular solution for this initial condition. So yours and mine might not look exactly the same, and that's okay if they don't, as long as I feel like yours is reasonable for the situation. So what should I see? I should see the graph rising, and I should see it going toward that slope field. How sharply it rises? Well, I might have thought it went out this way a little bit more. This is kind of like dropping a penny in a current of water. It goes with the flow. You go with the flow. It's not a precise science here. So the population increased rapidly, I would say, at first. Pretty quick. But then it levels out. Flattens to 8,000 fish. So if you start with 1,000 fish in the lake, their numbers are going to increase, and they're going to keep increasing till they get to 8,000. And then once you have 8,000 fish in the lake really can't sustain more than that. They're going to die off. So you're just going to end up with about 8,000, and that's it. Okay, when is the rate of increase in the fish population the greatest? Okay, when is the fish population the greatest? Well, that's going to be at that point of inflection, which we can find the y coordinate of by doing the upper asymptote, which is 8, minus the lower asymptote, which for population is 0, divided by 2. So that's 4,000 fish in the lake. Now, they didn't ask what's the population when the rate of increase is the biggest. They asked when, the time. So let's see, 4,000, 2, 3, 4, that's right about here. Let's see, on my graph, that looks like the time of about 2. But we talked about how it might have been a little bit more off this way, so that's getting close to 3. Probably between 2 and 3 years would be reasonable there. And if you put 2 years or if you put 3 years, those would be fine answers when you're using the slope field to make that judgment. Now, verify this using the differential equation. So here's my differential equation. How could I verify this using the differential equation? Well, we could substitute the y value, which is the number of fish in the lake, with the 4,000 to verify that. Or, oh no, you know what we could do? We could set the second derivative equal to 0. Second derivative equals 0, that would for sure tell us if we were on the right track here. So this is the first derivative. If I wanted to find the second derivative, I'd probably first want to simplify this first derivative equation. Let's say 0.8y times 8 divided by 8 would be 1 minus 1/8 y. Yep, and now I could distribute. So this would be 0.8y times 1, and then 0.8, let's see, minus 0.8 over 8y squared. What is 0.8 divided by 8? 0.1. So 0.8y minus 0.1y squared. There's your second, oh no, that's your first derivative equation. So the second derivative, d squared y over dt squared, is, oops, sorry. The derivative of 0.8y is 0.8, and the derivative of 0.1y squared would be 0.2y. Okay, so the second derivative equals 0 when the population is increasing the greatest. So I'm going to add my 0.2y to both sides. 0.2y equals 0.8, divide by 0.2 on both sides. So y is equal to 4, and remember y is measured in thousand, the number of fish in thousands. So this is going to give you 4,000 fish as the number of the fish population when the rate of increase is the greatest. But still, we're only going to be able to use our slope field to judge that time kind of roughly. All right, part C. Suppose that at the time, let me see if I can move this a little over. Suppose that at the time 4, the lake is restocked with fish. Is that a thing? Do people restock lakes with fish? Yes, they do. Bringing the total population up to 11,000. On the slope field, sketch the particular solution subject to, that should say this, not his, this initial condition. Describe what happens to the fish population as time goes by. Okay, if I throw 11,000 fish in the lake at time 4. So here's time 4, 11,000 fish. I'm right here. I just drop them in the lake. The population will drop pretty rapidly till it reaches a leveling off point at 8,000. So this could be valuable information for somebody who's working with wildlife populations, maybe like biologists or conservationists, or, you know, anyone who studies life populations of animals or creatures over time. The population decreases and levels off to 8,000 fish. So that describes what happens to the fish population as time goes by. All right, now you know about logistic growth equations and you've got some practice problems to work on. I hope you have lots of fun and learn a lot, and have a wonderful day. Bye for now.